All right, first of all, I would like to thank the organizers for giving me an opportunity to talk about imaging the surface, atmosphere, and the innermost circumstellar environment of stars, which turned out to be quite complex, more complex than we thought. Well, at least that I thought. So the last part of my talk is about the observing stars as we observe the sun. And at least to me, the goal is to better understand the fundamental physical processes like convection, pulsation, magnetic fields, onset of stellar winds, and dust formation. And the imaging stars other than the sun provides us with new possibilities to test theoretical models and obtain new insights. So what's shown here is the beautiful image of sunspot and granules. And I think we still have a long way to go to achieve this level of resolution. But if we observe star spots other than the sun, like this RCV and star Zeta Andromeda published by Rachel Rottenbacher, we can study the magnetic field generation mechanism other than the sun. So from the talks of this morning session, the imaging convective cells serves as test for 3D models. And as far as asymptotic giant bright stars are concerned, comparison of the cell size and the contrast with 3D model looks promising. And what's shown here is the AGB star Pi1 group published by Palladini et al., taken in the H band. So the surface shows a few large convective cells whose size is about a quarter of the stellar radius. And these convective cells might be the cause of clumpy dust formation recently seen in the scalar light images. For example, this is the polarized intensity map of the nearby AGB star W Hydra, taken at 645 nanometers. And you can see a couple of large dust clouds close to the star. Well, and these clumpy structures can be seen in the gas tube if we take advantage of the high spatial resolution provided with ALMA. So what's shown here is the ALMA imaging of the same AGB star W Hydra, and we got the ALMA data in the band 6 near 250 or 260 gigahertz with a maximum baseline of 16 kilometers. And with this setup, we can achieve a resolution of about 20 milliarcsecond, which is basically comparable to the previous image of the sphere data. And the data were reduced by cap.1 at IRAM. And what's shown here is 3 channel max at the 3. So this is the systemic velocity and the blue shift and the red shifted. And at this SIO line, we can probe the layers quite close to the star. And this one a little farther out. And with this one, we can see very complex structures. Like here, we see some plume, and also there is a tail here. And you can see that absorption, by the way, these are the continuous subtracted images, and of the stellar disk, you can see inhomogeneous absorption. And the other one, the SIO line. And the last one is SO2 line. And what's interesting about this line is we can see emission of the stellar disk. It should be absorption usually, but then the emission of the stellar disk means that there is hot gas in front of us. So we are still analyzing the data, but then this emission of the surface might be hot gas heated by shocks. So if we go to other wavelength domains, we can see the complex structures of the atmosphere. What's shown here is the Betelgeuse image taken with HSD in the ultraviolet, and this image shows the hot chromosphere. This black circle is the size of the star, of the optical stellar disk, and obviously chromosphere is extended to 2 to 3 stellar radii. And this is a more recent image taken by Cabell et al. the Betelgeuse image in the H alpha line, which also originates from the chromosphere. So from this image too, it is obvious that the chromosphere is extended to 3 stellar radii. The right panel shows the 7mm image taken with VLA, which shows cool neutral gas at 1000 to 4000 K. So this image and this chromospheric gas image are shown in the same spatial scale. And we can overlay the more recent ALMA image taken by Ogoma et al. At 338 gigahertz, and it also shows extended atmosphere, and there is some localized heating spot here. So obviously the cool neutral gas or molecular gas and the chromospheric gas are coexisting within the 2 or 3 stellar radii. So possibly hot plasma has a small filling factor and is embedded in the cool gas. But this hot gas is not limited to the red supergiant. It's also present in AGB stars. So the left panel shows the same AGB star W Hydri taken with ALMA in the 338 gigahertz continuum by Fleming et al. And they found a hot spot here over the stellar disk. The right panel shows the Myra. It's a binary system, A and B, and A is the AGB star, and B is a hot companion. Actually, this image Chandra soft X-ray image taken by Karovska et al., and they found an X-ray outburst associated with Myra A, the AGB star, not the hot companion. So this understanding this multi-component nature, the cool atmosphere, cool star's atmosphere with a hot gas can be a key to solving the stellar wind acceleration mechanism. And also, in general, it's important for comprehensive understanding of the atmospheric structure of cool evolved stars. Now, what I want to show here is a recent work led by Ogoma et al., which is the VLA and ALMA imaging of the red supergiant Antares. And the idea is, using the multiple frequencies in the radio, we can plot the temperature structures from the photosphere, layers close to the photosphere, to outer atmosphere, and to the innermost circumstellar envelope. And they observed Antares at 14 frequencies from 7 to 405 gigahertz. And as we will show now, higher frequencies allow us to see or probe layers closer to the star. And these data, multiple frequency data, allow us to get temperatures at different layers. So what's shown here is the VLA image taken at the 3 gigahertz, and Antares is a binary system. So this is Antares red supergiant alpha score A, and alpha score B is here. It's a B star type main sequence. So what's we see here is actually the circumstellar material from alpha score A, the red supergiant, but ionized by the hot companion. Now, if we move to higher frequencies, 5 gigahertz, this ionized zone is weaker. It's even weaker. And at 13.5 gigahertz, we can't see it anymore. So now we zoom into this red supergiant alpha score A. So at the 16.5 gigahertz. So this is the beam size. So the alpha score A is slightly larger than the beam size. So this spatially resolved. Now, if we move to higher frequencies, 22 gigahertz, it looks smaller. 33 gigahertz, even smaller. 44. And now we switch to ALMA, 97.5 gigahertz. 145, 343, and 405 gigahertz. So at higher frequencies, the star is smaller because the opacity decreases with frequencies. And as we have seen, the beam size is only slightly smaller than the star, so we cannot see detailed structures of the surface. Nevertheless, we can derive temperature at different layers and which is shown here. The x-axis is the radius from 1 to 10 stellar radii, and the y-axis is the gas temperature. The red symbols are for Antares, and the blue symbols are for Betelgeuse. And they both show a similar trend. Near the surface or near the photosphere, the temperature is about 27 or 2800 K, and it goes up to nearly 4000 K, and then it goes down. So this looks like a chromosphere. However, the UV emission lines do show really hot chromosphere at temperatures of 7,000 to 9,000 K, or even hotter than 12,000 K. So compared to this real hot stuff, what was found with ALMA and the VLA is not so hot. So it's a lukewarm chromosphere with the peak temperatures of 3,800 K. So at least we have two kinds of chromosphere. But if we go, we combine ultraviolet, infrared, and radio, the situation looks even more complex. So we have hot chromosphere and lukewarm chromosphere, and the near-infrared interferometry has revealed the presence of warm molecular gas, or the so-called mole sphere, at a temperature of about 2000 K. But recently, Ovo et al. Used the near-infrared aperture masking polarimetry and found the dust formation very close to the star, like 1.5 stellar radii. This means the presence of gas, dust forming cool gas with temperatures lower than 1500 K. Otherwise, the dust cannot form. So if we put all these things together in a figure, it looks like this. Here is the stellar radius and the gas temperature, and these blue and the red symbols are the lukewarm, they represent the lukewarm chromosphere seen with the VLA and ALMA. And this past rectangle represents the temperature and the radius of the near-infrared CO atmosphere of this warm molecular gas. And this arrow shows the upper limit of the temperature constrained by the dust formation detected by aperture masking polarimetry. So at these radii, near 2 stellar radii, we have everything. This is the lukewarm chromosphere and hot, really hot chromosphere, and this molecular gas and the cool dust forming gas. So the question is, how is it possible, especially if we take a look at the near-infrared images of Antares. So these are the images taken with the VLDI amber in the 2.3 micron CO lines. The left panel shows the image reconstructed in the CO line. We can see two bright regions over the surface and the irregularly shaped extended atmosphere. And the right panel shows the velocity map derived from this amber data, the high spatial and high spectral resolution amber data. So red and orange region mean that the gas is moving toward us at 220 km per second, while the light blue and blue region mean that the gas is moving toward us at 20 kilometers per second. So obviously there are a lot of large gas clumps, and they are moving up and down in a very turbulent way. However, there are no, say, holes. So there are inhomogeneities, but there seems to be little room for the lukewarm component that we see in the ALMA and the VLA data. So how can we accommodate the 4 different components with distinct, very distinct temperatures? And maybe cells may be smaller than the resolution of these amber images. Oops. These amber images, which is the 5.4 milliarc seconds. So as schematically shown here, lukewarm chromosphere is distributed like this rather uniformly, but each cell or each pocket is very small. And the same is true for the molecular gas, distributed uniformly, but in small pockets or cells. and also the hot chromospheric gas. So if we see them together like this, they also all the components have the same global, say, scale. But if we take a look at the smaller scale, then we might be able to see inhomogeneities. So to prove or disprove this idea, we have a gravity imaging program for Antares approved in the same way in the CO bands, but this time with an angular resolution twice better than the previous observations. And if we combine this with HHT's observation of the ultraviolet CO electronic bands, which are actually being reduced, executed this week. So when I thought about this picture, just remember this famous painting of the pointillism by George Seurat. And if you take a look, this is a tree, and if you take a closer look at this, well, at every position you can see the points with different colors. So we hope that with the gravity and the HST data, we may be able to prove or disprove this pointillism scenario for the outer atmosphere of the supergiants. Well, now I would like to turn to another supergiant, but this time much dustier than the Betelgeuse or Antares, and also the outside the Milky Way galaxy, namely in the Large Magellanic Cloud. So this is the infrared image of the Large Magellanic Cloud, and our target, WOHG64, is here. And actually, in 2008, we observed this supergiant with VLTI MIDI at 8 to 13 micron, and we measured the angular size at different position angles. And it was the first, and I guess it still is, only the individual star spatially resolved in an extragalactic system. Anyways, we carried out 2D radiative transfer modeling to explain the observed SED and MIDI data simultaneously, and found out geometrically and optically thick dust torus seen pole on came to the job. So the left panel shows the SED from the optical to far infrared, and the torus model, the solid line can explain the observed SED quite well. And the right panel shows the MIDI data. So from 8 to 13 micron, the symbols with different colors the measured angular diameters at the different position angles. So they don't differ so much. And this is well explained by the torus model, because as you can see here, this torus model image, if we see the torus from ball on, the angular side doesn't depend so much on the position angle. So we were quite happy about these results back in 2008. Now, in December 2020, we went back to WTG64, but this time with gravity and with AT. So media observation that I showed in the previous slide were done with UTs. And it worked out. And I just want to note that the G-band magnitude of this target, 14.8, is really at the limit of AT's adaptive optics system, Naomi, 15 magnitude. But it worked out thanks to the great efforts of the VLTI team on Paranal. And we reconstructed images. The left panel here shows the image reconstructed with NIRA, and the right panel shows the image reconstructed with IRBIS, done by Karl-Heinz Hoffmann at the Max Planck Institute for Radio Astronomy in Bonn. So basically, both images show similar structures. And first, this elliptical ring, 10 by 5 milliarc seconds here. And this can be interpreted as the dust disk's inner rim. And what's puzzling here is this one. This is the inner emission, elongated emission with a size of 3 to 2 milliarc seconds. And we are not sure about the nature of this component. Maybe it's an elongated dust or gas envelope or cocoon, and elongated due to a companion in the equatorial plane of the disk, or it might be a bipolar outflow perpendicular to the equatorial plane. And if we compare with the observed image with the image predict from the previous torus model at 2.25 micron, they don't look very similar. Actually, they look quite different. So maybe our torus model, which was based on the metadata, was too simplistic because we had only 4 metadata points at 4 different position angles, but at the same projected baseline. Well, that is probably partially true, but maybe there is another reason, which is the time variation. Because we found a significant change in the infrared spectrum of WOHG64. So what's shown here is the spectrum from 1 micron to 4 micron. And the upper panel shows relatively old data, the photometry and SOFI data spectrum, and the ISO and speedo data. So these data can be explained by photospheric spectrum with water vapor absorption here and here. The lower panel shows the spectrum data relatively recently taken. So the green line shows the extruder spectrum taken in 2016, and the orange is the spectrum extracted from the gravity data 2020. So they are consistent, but if we compare this part and this part, the difference is obvious. Now we have the very spectrum monotonically increase in spectrum. This means the stronger dust obscuration started somewhere between, say, 2003 of SOFI observation and the extruder observation in 2016. So maybe this the recent the time variation can also be responsible for the difference between the torus model, previous torus model, and observed image. And we are working on the modeling of this object. So the point is this ring might be reminiscent of the more famous ring of a supernova 1987A, which also happened in the Large Hadron Cloud. And of course, the progenitor of the 87A was a blue supergiant, not red supergiant. But this ring of material was ejected in the red supergiant, preceding red supergiant phase. But I'm not really claiming that the WHG64 is the progenitor of a supernova like 87A, but my point is this. So imaging red supergiant innermost circumstellar matter is complementary to the circumstellar matter study inferred from the supernovae, because nowadays it's possible to get the very early phase spectra of supernovae. Very early phase means within a few hours to within a few days after explosion. So these data allow us to see the circumstellar material close to the progenitor star. So the last phase of last phase just before the explosion. So this is the red supergiant study is very complementary and bridges to the supernovae research. So this is the summary slide. So the multi-wavelength approach allowed us to reveal the complex multi-component nature of the outer atmosphere of coolly evolved stars. And we need higher spatial resolution to prove or disprove the pointillism idea. And I would like to mention that ALMA's high frequencies at long baseline allow us to get spatial resolution, which is high enough to resolve dynamical atmospheres. And the last point is something personal, but say also mentioned by Marcus Witkowski. There seems to be a group of coolly evolved stars somehow unfairly neglected, or say not imaged so often. They are normal K and M giants. Normal means non-Mira red giant branch stars, or AGB, non-Mira AGB stars. They do have the outer extended molecular outer atmosphere and chromosphere, and they tend to have little or no dust. So in a sense, they may be simpler than say dusty AGB stars. So the imaging those stars, normal red giants, might also help us to understand the nature, the physical process behind the multi-nature of the outer atmosphere of cool-evolved stars. All right, so I stop here and thank you very much for your attention.
Thank you, Keiichi. So do we have questions? Online, maybe online. So we have a question from Marcus Witoskowski. How long life will you expect each such cell of a certain temperatures to be?
Well, short answer is I don't know, but then in the if it's say the cells are due to convection, I don't know, maybe say days or weeks. Maybe Andrea Cavassa can answer better.
So question, other question? What a question. Remember to say your name and your affiliation, please.
Hi, Keiichi. This is Miguel Montarges from Paris Observatory. I was wondering, in your opinion, what is causing these small cells that you see at different temperature with dust, the chromosphere? Because I think it would be smaller than the convective cell on the photosphere. So I was wondering what would be the mechanism creating such structure.
Yeah, but then you can exclude the convection from possibility, or if not, maybe magnetic field. But again, this there is not so much say theoretical models. So this is this is all that I can answer now.
So we have a question online. Yinhua, go ahead.
Okay, and so I think the elliptical shells in the LMC red supergiants is very interesting, but I want to know whether the fin structure, the shell-like structure is real, because you show multiple shells, but usually we know that in interferometry, we suffer from some side lobes or residual side lobes in the images. I want to know if those faint shells are all real structures or just noise or residual interferometry effect. Yeah.
So
yeah,
you mean
this one, for example. Yeah.
This one? Okay, so
yeah.
I don't trust these things. I don't trust these things.
Yeah, but you don't trust it. You trust the innermost one, right?
Yes, because they appear in the both the independent algorithm.
Here. Yeah, but the outer rings are also nearly parallel, right?
Yes.
So I don't know which one is real. How to judge it?
Yeah, but then, for example, this one appears here, but then don't appear here. So I don't think this is the. Also, they are quite weak, so they don't think they. I don't trust these things.
Yeah, but their strength is similar at the innermost one.
Sorry.
Then the strengths of the outer rings are similar at the inner ones. So I suspect that maybe they could be the side lobes of the interferometers.
Yes, but then we have this because this is constrained by these things are constrained by the short baseline data, and then we simply remove this. Then we can't explain the visibility data.
Okay, thank you.
So once again, Keiichi.